Students, now we are going to see Gaussian mixer model, that is GMM, and expectation minimization algorithm, EM. So what is GMM? It's a probabilistic model that represents data as a combination of several Gaussian distributions, each with its own mean and variance weighted by a mixing coefficient. These are commonly used for clustering and density estimation since they can capture complex multimodal distributions where data points may naturally group around different centers rather than a single mean. This model is a probabilistic model. So, and the model, how it works. It has many real-world applications beyond clustering, segmentation, density estimation, anomaly detection, and pattern recognition. All can be approximated by a Gaussian mixer model. Here is a challenging distribution that is clearly not Gaussian. So a non-Gaussian distribution. Normal distribution curves are here. So a two-dimensional Gaussian plotted using a contour plot. So when it is used as a clustering algorithm, each Gaussian in the mixer model has three key parameters: the mean vector, covariance matrix, mixing weight. Okay. So how to fit a GMM model? So first we have to find the parameters, mean variance of each Gaussian. Then find which Gaussian each data point likely belongs to. There is a hidden variable is set. That variable tells which Gaussian created a data point. So we cannot see Z directly. It's a hidden value. We only observe the data point X. So GMM uses the EM algorithm, expectation minimization algorithm, to estimate the probability of each possible Z. So mathematically, the probability density function PDF of a data point X under a GMM with the K components is PDF, that is probability of density function of X equal to sigma K equal to 1 to K pi K into N of X with respect to mu K sigma K. So this shows how much this Gaussian contributes, that is the size or importance of cluster. So expectation minimization algorithm, it is a GMM is trained using the EM algorithm. E step indicates find probability of each point belonging to each Gaussian. M step denotes update mean, variance, and weights. We use EM because the log likelihood function is complex and nonlinear. So maximum likelihood expectation cannot solve it directly. Also, GMM has hidden variables. They are not visible in data. These are not visible in data. So MLE alone cannot handle them properly. While we using EM algorithm, it handles hidden variables easily and can be parallelized. That means the process will be faster for big data. EM consists of 4 steps. First, initialization. EM starts with random guesses for parameters, mean, variance, and weights. It assumes data comes from some Gaussian mixer model. So ways to initialize, we use k-means and use random values and pick values from training data. So in the expectation step, we compute probability of each data point belonging to each cluster. Then first we have to posterior probability of each latent variable is calculated based on the observed data. The probability that Zi equal to k, that is that xi belongs to the kth component, can be computed using Bayes rule. So Q function can be calculated. Then in the M step, it updates three distinct values for each Gaussian distribution. Mean update typically represented as mu, then updating the covariance matrix, then updating the mixture weight. From that, the new value will be calculated. Finally, the M step updates the mixer weights. So after updating the weight, finally EM checks that model parameters are stable and converging. If the changes in log likelihood or parameters are below a set threshold, then the algorithm stops. If not, then the process will repeat the iterations of step 2 and 3 until convergence is reached. These are all about GMM and expectation minimization algorithm. Thank you.